The today periodic table we use is the modern periodic table based on the Mendeleev. Almost the same, the form or the shape. Here we have column, that is group, and then here we have a row. Row is a period, so we have 7 period. This is hydrogen and helium in period 1, row 1. Row 2, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. That's a period 2. Until this is period 3, sodium, magnesium, and so forth. So here, the last is period 7. For group, the purple one, this is group 1. The brown, this is group 2. You have the number in here, that's the number of group. That's the new way to name the group. The old way is group 1 we call as 1A, group 2 as 2A, and then from 3 until 12 that transition metals, or a block D elements, and then 13 is 3A, 14 or 4A, 15 5A, 16 6A, 17 7A, and here is 18, that's 8A. This one is 8A. So you have here how many groups? Group 1 or 1A is alkali metals, and then group 2 is earth alkaline metals, and then you have group 3 until group 2A until group 8A. This is the main group. So group 1A, 2A, 3A until 8A, or 1, 2, 13, 14, 15, 16, 17, and 18, that's the main group. Then from group 3 until 12, that's the transition group. So here we have main group, group 1, 2, and then 13 until 18. Yeah. For group 17, the name is halogen. 17 is halogen. And 18 is noble gases. Noble gases. For transition group, divided into 2. The first is outer transition group, and then the second is inner transition group. The inner transition group, there are 2 series. Lanthanide series, this one, the green line here, and then actinides is the orange. The position of the lanthanide, the green, is in this behind lanthanide element here. Lanthanum 57, that's the name of element. So here the elements are ordered, arranged based on the atomic number. You notice here barium is 56, and then you have lanthanum 57, but after lanthanum then jump into 72 hafnium. So there is gap in here from 57 to 72. Actually, this are the elements of lanthanide, 58 until 71, lutetium, cerium until lutetium. So the position of lanthanide inside or behind the lanthanum in here. So this series of lanthanide is inside the group 3. For actinide series, the yellow, you notice here actinium, the number is 89, actinium. Actinium is the name of element. And then after 89, and then jump to rutherfordium with proton number 104. So there is gap in here. The elements in here is actinide, starting from thorium number 90 until lawrencium number 103. 103. So we have here inner transition in group 3, period 7, behind element actinium, proton number 89, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there are 14 here in here, 14 elements behind actinium. Then we can classify or divide the elements into block. Block S is for a group 1 or 1A with the electronic configuration ended up with NS1. And then group 2 or a 2A, earth alkaline, this is alkali, NS2. For example, lithium number 3, the configuration is 1s2, 2s1. So the N in here for lithium is 2, and then the subshell is S1. For group 2 or group 2A, earth alkaline, for example Mg, proton number 12, the configuration is 1s2, 2s2, 2p6, 3s2. So right here, for a magnesium in group 2A, the configuration ended up with 3s2. So in general, for group 2A, the configuration ended up with NS2. For magnesium, the N is 3, meaning that the magnesium element located in the third period or in the third row. For a block P, that is for a group 13 until 18, or from group 3A until group 7A. The configuration for group 3A ended up with NS2 and P1. For group 8A or 18, the electronic configuration ended up with NS2 and P6. So for aluminum, for example, in group 3A or 13, aluminum is proton number 13, and the configuration is 1s2, 2s2, 2p6, 3s2, 3p1. So the number here, the electronic configuration ended up with 3s2, 3p1, or in general, for group 3A is NS2 and P1. For aluminum, because N is 3, meaning that aluminum is located on a third period. Block D is the transition. So here the block D elements is group 3 until 12. For a block F is lanthanide and actinide series. So here once again the main group 1 or 1A, that's alkali metals. Group 2 or 2A is earth alkaline metals. For group 1 or 1A alkali metals, we have lithium, sodium, potassium, rubidium, cesium, and francium. Francium is radioactive. For group 2 or 2A earth alkaline metals, we have beryllium, and then magnesium, then calcium, strontium, barium, and radium. Radium is a radioactive. For group 13 or 3A until 15 or 5A, the name of the group we can say as the name of the element. So group 13 is group of aluminium, group 14 is group carbon group, and 15 of 5A is nitrogen group. Group 16 or 6A, chalcogens. Group 17 or 7A is halogens. And then 18 or 8A is noble gases. For chalcogens or 6A group elements starting from oxygen in the second period, and then we have sulfur, and then selenium, and then tellurium. For halogen, fluorine in period 2, and then chlorine, and then bromine and iodine, and then the last is astatine. Noble gases starting from helium in period 1, and then neon, argon, krypton, xenon, and radon. Radon is radioactive. So once again, group and configuration. Group 1 ended up with NS1 for the configuration. Group 2 ended up with NS2 that we name as block S elements. And for group 13 until 18, the electronic configuration ended up with NS2 and P1 until 6 that we name as block P elements. Group 3 until 12, the electronic configuration ended up with NS and then N-1 D or block P elements. For example, for manganese 25 Mn, the configuration is 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, and then 3d. Here you have 2, 4, 10, 12, 18, 20. The proton number 25, so 3d 5 in here. So the electronic configuration ended up with 4s2 and 3d 5. So ns and then n-1 d. The atomic number 58 until 71 from cerium to lutetium, that we call as lanthanide series in block F, and 90 until 103 from thorium to lawrencium we call as actinide series, that's is block F elements. We continue with the periodic properties we want to discuss. For things, the first is ionization energy, the second one is electron affinity, the third is atomic radius, and the fourth is electronegativity. In this figure, we can see the trend of the fourth and non-metallic and metallic character or properties. For ionization energy, the direction of the arrow indicates that the ionization energy from left to the right is increasing. So the ionization energy of hydrogen, for example, in here in group 1 is lower than the that of helium. For atomic radius, the atomic radius for hydrogen compared to lithium in the second row or second period is lower because the atomic radius going down the group is increasing. For a non-metallic character, you can see here, so going across a period, the top one is the most non-metallic character. For the metallic character or the very reactive metal is in this left bottom. For the atomic radius, the biggest shell number, so the biggest period, and then on the left hand side, because going across a period, the number of proton and electron is increasing. Because the number of proton and electron increasing, then the electrostatic force between the positively charged nucleus and the negatively charged electrons in the outermost shell of the atom increasing. Then the energy uh, needed for ionization energy is increasing, and the atomic radius decreasing. Why decreasing? Because the electrostatic force between the proton positive and electron negative in the outer shell of the atom increases. So the atomic radius with the same number of shells decreasing. What is ionization energy? Ionization energy is the energy required or needed to remove an electron from a gaseous atom or ion. For example, we have sodium. We have sodium with proton number 11. The configuration is neon. That's number 10. And then continue with 3s1. So for sodium to release the valence electron, we'll need first ionization energy. We can write the equation from atom, neutral atom, sodium, release one electron, then the sodium changes into Na plus because the one electron from the outer shell of the atom is released, this one. So the sodium become a positively charged ion Na plus. Then this energy delta Hi, that the energy or ionization energy the energy needed to release one electron. Why the energy is needed or required? Because between the positively charged nucleus and the electron in the shell here, in the shell, there is attraction force to be released, then the atom should overcome the attraction force between the positively charged nucleus with the electron. So the energy is needed. This is for the successive ionization energy. For sodium, the electron, valence electron only one. Then in normal condition, sodium only release one electron from a neutral atom. Then for sodium, only need a first ionization energy. But for a magnesium, with proton number 12, the configuration is 1s2, 2s2, 2p6, 3s2. So Mg actually need to release two valence electron or two outermost shell electron. Then from a neutral atom Mg will form Mg2 plus because there are two electrons released. Then two electron release. So for a magnesium atom to be magnesium 2 plus ions should release two electrons. So we'll need two type of ionization energy. The first is first ionization energy. We can write the equation as Mg to be Mg plus electron. And the second one, to release the second electron. So the second electron will come from Mg plus. So the second ionization energy, we can write in equation Mg plus to be Mg2 plus E. So the second ionization energy is the energy required to release the second electron. And then we can subtract here, or we can add, and then here Mg plus on the left, the same as Mg plus on the right. We can cancel out. So we have on the left hand side of the arrow, we have Mg, and on the right hand side of the arrow is Mg2 plus 2 electron. So here the energy in here, or delta H in here, is a first ionization energy and the second ionization energy. So the successive ionization energy is the energy needed to release one by one the electron. For example, for aluminum with proton number 13, we can write the configuration in a simple way in noble gas form here. Neon is number 10 in the second period, so we'll continue with 3s2 and then 3p1. So here the outermost shell is the third shell. Then the electron, the valence electron is 3. So aluminum needs to release 3 electrons to be stable, just like noble gas neon. So aluminum will release 1 electron to be Al plus, and then Al plus will release 1 more electron to be Al2 plus. Al2 plus will release 1 more electron to be Al3 plus. This is a successive ionization energy. First, second, and third ionization energy. This 3 ionization energy needed to change aluminum atom to be Al3 plus ion. So there are 2 electrons on the right hand side, and here the same. This means cancel out. So this is what we have. This is the ionization energy, first, second, and third. That's successive ionization energy of aluminum. We continue with electron affinity. Electron affinity is the amount of energy released when an electron is attached to a neutral atom or molecule in the gaseous state to form a negative ion. So this is the opposite of ionization energy. Ionization energy is for a metal, especially to form a positive ion and then release electron. This is ionization energy. For electron affinity, the opposite of the ionization energy. So electron affinity happen to non-metal. Non-metal. This is happen to metal. Non-metal will take electron to form a negatively charged ion. For example, Cl number 17, electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p5. So the last shell is the third, and the valence electron or the outermost shell electron number is 7. So to reach a stable electronic configuration, just like a noble gases, chlorine needs 1 electron. So after added with 1 electron, then the number of electron is 18, but the number of proton plus is still 17. So in general, the Cl atom right now become negative 1 ions, like that. The energy that is released here, we call as electron affinity. Continue with atomic radius. The distance from the center of the nucleus to the outermost shell containing electrons. So going down the group, because the number of shell added, then the atomic radius from one group going down the group from top to the bottom, the atomic radius increases. Or in other words, atomic radius is a distance from the center of the nucleus to the point up to which the density of the electron cloud is maximum. The last is electronegativity. This is a measure of the tendency of an atom to attract a bonding pair of electrons. For example, H and Cl. Here there is a bond pair between H and Cl. Cl is in group 7, so the valence electron is 7. When sharing with 1 electron from hydrogen, then chlorine will complete or octet. For hydrogen become duplet, similar to helium. For chlorine, similar to argon. Then the electronegativity scale proposed by the scientist named Pauling. The most electronegative element is fluorine or F. The value of Pauling scale is 4.0. For francium, that's the most electropositive element, or the least electronegative element, francium. The Pauling scale is 0.7. For fluorine, because this is the most electronegative element, then for fluorine there is no substance or compound in which the oxidation F is positive. So fluorine always -1. For example, NaF, the oxidation state of sodium is +1, the oxidation state of F is -1.